Let's say that we have several bodies. Let's call these bodies M0, M1, M2, and M3. And let's solve for the gravitational interaction between them. Let's choose an origin. So the origin would be a point here, a point O, and the vectors to these bodies, R0, R1, R2, and R3. We can write the sum of the forces. For any body I, the acceleration is going to be Ri dot dot is equal to the sum of the gravitational accelerations of the other bodies. But now let's consider that M0 dominates the mass budget. And because of that, let's set M0 as the primary. Let's measure now then the coordinates with respect to M0. So for coordinates with respect to the primary, let's use lowercase r. So these would be lowercase r1, lowercase r2, and lowercase r3, where by definition, the lowercase are the positions with respect to the primary. So big R of I minus R0. And according to this definition, then little r0 is equal to 0. So we can now set what the accelerations with respect to the primary are. The second derivative of little r is the second derivative of big R minus the second derivative of the primary with respect to the origin. So we substitute first what we defined for the second derivative of a big R. And for the second term, let's substitute i's by zeros. So that then becomes minus j of the sum of j not equal 0 of mj. Now big Rj minus big R0, let's substitute it by our notation here with little r, and that becomes simply little rj over the cube of the modulus of little rj. Now, because we are treating the primary differently, let's extract the primary from the first summation. So let's use then here first j equals 0. So that becomes g times m0. Now the numerator here is r0 minus ri. So that's the negative minus little ri. So that gives you a minus sign and that little ri here. Same thing in the denominator, the modulus of little ri cubed. And then you can do summation, avoiding the 0. So starting the counter j from 1. So j not equal to I, and starting from 1 to n. Let me just change the notation here. So j from 1 to n, and also j not equal to I. And then the last term, you can start then, since it's simply j not equal to 0, you can start that counter also from j equal 1. So these two summations are almost the same, except for the fact that the first summation avoids j equal I, whereas the second one does not avoid j equal I. So let's get the j equal I out of the second summation. Then this term would be the same term, but now do j not equal to I, and then write the term with j equal I separately. So that would be mi ri over the modulus of ri to the cube. Now notice that the first term and the last term have the same form. They both have ri vector and are divided by the cube of the modulus of ri. The only difference is the masses. The first one has m0, which is the primary, and the last one has mi. So let's group it together. So grouping the two terms together, the first and the last, this becomes minus g of the sum of m0 plus m1 times r1 vector over cube of the modulus of ri. And now for the summation terms, they are all the same argument of the summation, j starting from 1 to n and avoiding j equal I. So we can put them under the same summation. And just to simplify the notation so that we don't carry the capital R's, notice that these are just reference positions, rj minus ri, with respect to the origin, but because they're just relative positions, they are identical to the little r. It's the same vector. So let's put everything under the little r notation. And here we have our separation. We have the first term here being the two-body problem, being only the sun and the body I, as if they were the only two bodies. So the first term captures the two-body motion. The second term, the summation, is the perturbation. And notice that there are two terms inside of this perturbation. The first one is obvious. It's the gravitational attraction of all of the other bodies in the system. So this would be the bodies mj that are perturbing the body mi. So that's the first term in the perturbation, is the attraction from all other bodies. The last term is less obvious. The last term is an inertial term that comes from the fact that we switch the reference frame from the origin to the primary, and the primary is moving because of the gravity of the other bodies. We are in a non-inertial reference frame. This term is an inertial term. So this term here is the acceleration. This last term is the acceleration of the primary as a result of the gravity of all of the other bodies combined. We call this the indirect term to refer to the acceleration of the primary. It's because the central mass is outside of the primary and the primary itself is orbiting around the central mass.